Ed is one of the first people to be certified in Passive House standards. Isn't that right, in Canada?
Yeah, I was one of the early people trained by the Passive House Academy in the U.S. Second one in Canada.
He's the owner and operator of Passive House Ontario and lives down the street in Oakville. What else can we tell about you? Well, you have been, since the 2008, the first Passive House conference in Duluth, Minnesota, and you was inspired initially by people who were able to heat their houses with hair dryers. Talk a little bit about that.
Yes.
And where do you work? Where's your company cover?
I work wherever someone will hire me, chiefly in southwestern Ontario, but I like Oakville.
There we go.
There we go. So that's great. Thank you very much. I'll put my glasses on here so I can see my screen. So yeah, my name is Ed. I run Passive House Ontario. I've been involved in construction for most of the 2000s in Oakville. Starting off working in big custom homes and did that for a while. Now the common denominator of all these homes was that they all had 2 furnaces and 2 air conditioning systems. And at some point I realized it's probably not a good idea, probably not a very sustainable model for building. And I came across in my travels the Passive House concept, homes you can heat with a hairdryer, if you can imagine that. So, to someone who's used to building homes with 2 furnaces, 2 air conditioners, it's kind of a radical concept. But the design principles are out there. They have started to take shape here in North America for pushing 8 or 9 years now. This is what I want to share with you tonight is basically the story of the first project that I did, which happens to be my own residence. I've done a number of high performance builds over the past number of years, but this is my principal residence, and I want to share with you some insight as to how it was built and to what it's like to live in it, including some actual data that I've been collecting. So. Following on the heels of what Greg was saying, basically I used the Passive House toolkit as the compass for this particular build, and so I did a training program in 2009, and I had a lot of knowledge, a lot of enthusiasm, but no experience. So my wife and I decided that we would use our house as basically a learning boot camp. So this is what we did. So this is the house pre-retrofit, is built in 1957. Typical 1,000 square foot bungalow, solid brick construction. Not very comfortable, except for a couple of times per year. Too hot in the summer, freezing cold in the wintertime. And we decided that we would change that. So this is it post-retrofit. You can see we increased the square footage. We basically made it a story and a half. You can see by the picture on the right-hand side that there's a dormer across the back. Here's kind of how we got here. So the first thing I want to talk about is energy efficiency, and think about it as a house's miles per gallon. Not so much the mechanical system, but the house itself. How easily does this particular house retain heat? Think of it as miles per gallon. So if you look at the column on the left-hand side, that represents stock average, and that's maybe even being generous. A lot of the older home stock would use a lot more than 150 kilowatt hours per square meter per year to heat the house through the entire heating season. As we move to the right, you can see that in the middle you've got the Energy Star standard, which is probably around 100 kilowatt hours per square meter. And this is NRCan data, by the way. I didn't make this up. Way over on the right-hand side, you have Passive House. So Passive House is a conservation-based approach that seeks to reduce the amount of energy used for heating by up to 90%. So it's quite a radical reduction, and it comes in at 15 kilowatt hours. So the yellow bar is my particular home, the Passive House retrofit in Oakville, and it's 35 kilowatt hours per square meter. That was the modeled using the Passive House modeling software. That's what it came in at, and some of the parameters have actually played out exactly as per model. For example, the heat load, the size of the mechanical system that was predicted by the Passive House design software is actually come in pretty much spot on. I have energy monitoring equipment at home that tells me it's one of the parameters that it spells out is what the maximum draw power was during the day, and it has definitely fallen within the the parameters of the Passive House predictions. The actual energy performance has actually exceeded what the program predicted. So we'll take a look at that as we go along. So, some of these concepts are not new. They just make part of the basic passive solar toolkit that has been around. Prior to the advent of fossil fuels and furnaces, people were probably, pretty careful about the way they built houses, and not through the use of energy modeling, but just through experience. They just knew that, well, if we build a house and put all the windows facing north and we live in a northern climate, it's probably not going to be a comfortable house. So they figured that out, and they realized that, solar access was an important thing. And in a lot of these climates, in the summertime, you can have too much solar access and get too hot. So the concept of a broad overhang is again, something that is not new and recently been invented, but it is something that's very useful. And in this particular house, it was modeled using the software as well as other sun angle type of information that was available. So this, for example, is the house in when the sun is at its steepest angle on June 21st. You can see how nicely the shading works there. So this is a super insulated house. When there's a lot of direct sunlight coming through the windows, it gets hot very quickly. Sure, you can intervene mechanically with a cooling system, and this house does have some cooling capacity, but far better if you can keep the direct heat right out of the house, and then you need much of a system at all. This is it in the wintertime on December 21st. So you can see it's completely bathed in sunlight, and the light penetrates right through to the far side of the house. This is it shining against the opposite side of the wall, against the other room. So there's a lot of direct sunlight in there. It has a very positive effect. On a very cold winter day, if it's sunny out, the heating system will not run until well into the afternoon when the house has gone around the corner. So, most houses can benefit from this. You don't have to live in a super insulated house for that. Anybody who has a home where there's a lot of wintertime sun coming in benefits from that sort of sun exposure. The difference being that if you have a really good building envelope to collect it in, that it's going to last a lot longer. It's going to create a much more comfortable situation. This is an older home that's basically been wrapped on the inside and on the outside with lots of insulation. So part of the consequence is that was very deep window reveals. You can't really tell by these photos that I've squished in here, but these are 20-inch thick walls, and there's a clear 12-inch shelf in front of the window that is actually quite nice. It really makes a lovely impact inside the house. The windows were a big job to do in this house. They were the single most complicated item, but they're also one of the features that we enjoy the most about the home. These are triple glazed windows, and the windows on the south side of the house have a higher solar heat gain coefficient, which is the attribute of a window that lets solar energy into the house. The windows on the north side have a lower heat gain but a higher insulating value. With windows, there's like this much to know about windows. I know like this much, I used to know this much, but with windows, you can't have it both ways. You can't have like a lot of solar heat gain and really good insulating value. It's kind of a trade-off between the two. So you have to find the right balance between these things. And in most homes, it never gets discussed anyways. The windows you get are the windows you get. But if you have the opportunity to think it through, to plan and to model, you can see what the benefit of the right window would be. This is the house under construction, so there's a continuous and generous layer of insulation around the entire house. If you're going to build a house and you want to reduce your heating energy by 80 to 90%, you're going to have to put more insulation on it than what the building code requires. This house was basically solid masonry, so it was one giant thermal bridge. There was virtually next to no insulating value in the house itself. So how do you mitigate that? If you just put insulation on the inside of the house, well, you're not going to have enough, and it's a small footprint house, so you really need to insulate on the outside as well. The advantage of it is that by insulating the entire exterior of the house like that, this is a 4 inches of EPS foam, is that not only have you added in the overall insulation value, but you've actually mitigated a lot of the thermal bridging that is inherent in the building itself. For those of you who aren't quite familiar with thermal bridging, so it's a construction detail, which most buildings have, where basically you have accelerated heat flow through that. So imagine the corner of a house where there's corner studs, there's no insulation there, you're going to have more heat loss to that part of the wall than an area where there's insulation bats, right? Anywhere we have steel beams supporting stuff that are near the outside, again, you have a lot of heat loss to those areas. So, in one particular spot, it might not be a lot, but when you collectively add these things up throughout the entire aggregate area of a house, it becomes quite significant. So if you pay attention to these things, you can really make a big difference on the heating impact. This is the new second floor of the house, so it has a triple layer we did a double stud wall there. So there's a triple layer of insulation bats in that wall, plus the exterior insulation. So these are R60 walls. There's actually a heat source on the second floor, but it almost never gets used. It's very comfortable in the summer and in the winter. This is the basement. The basement slab came out in the old reno, and we insulated underneath the basement slab with 3 inches of insulation, of foam insulation, that we then sealed, and basically we formed like a big styrofoam pan to pour the new concrete in. Now I didn't really, look at the energy loss parameters of a house until I got involved with this, but it's quite amazing how much heat is lost through the basement slab, and the comfort enhancement that this has created has been the most radical in all of the work that we did. So our basement is as comfortable as most main floors most of the year, all of the year in fact. If you were to be brought downstairs blindfolded and you didn't know you were going down the stairs, so let's say you could wake up downstairs, you wouldn't really know that you were in a basement. It's just very, very comfortable, and there's uniform temperature. There's no dampness. Everything has been very carefully air sealed, and so it's a really big return on the money and time that we invested there. This is the roof area that has a lot of cellulose insulation in it. It's up to, it varies because the trusses are different from place to place, but from R65 to R80. Very, very, very high level of insulation. Also leads to super quiet roof. We can't hear it raining. Unless the rain is hitting, driving right against the windows, you cannot hear it at all. Air tightness is a huge driver of heating and cooling loads, or air leakage rather. And so you have to pay attention to that sort of thing if you're going to build a low energy house. And basically, anywhere where there's a joint on a building, I'm not sure if the next, no I didn't, I took some of the photos out. So wherever there's seams in sheathing panels, wherever there's mechanicals, for example, you can see that there's conduits going in and out of the wall here for electrical, for the ventilation system, for other items. This is from a couple of different projects, different builds that I've done. You can just see the attention to detail of actually properly sealing the pipe. So this is like this is a very durable solution. It isn't just caulking around a pipe that's going to fail maybe within months of it being done. All of the projects that I do are modeled and designed around a certain air tightness goal, and the only way to verify that, as Greg was saying, is you have to test and measure. So we did a blower door test on this house. Passive house threshold is 0.6 air changes per hour, and this one was we were very happy with the air. This is our first kick at the can, and it was 0.63 air changes. I could round that off to 0.6. So this is a chart of comparable air leakage rates. So the stock average, probably 6.5 air changes per hour. And again, I think that's being generous, Greg. You've been in houses that have been way higher than that, right? Especially amongst the existing stock.
Even brand new houses.
Even brand new houses. So 1.5 was kind of the gold standard in Canada for the longest time. 1.5 air changes is the R2000 one. You can see that the center red band is Passive House at 0.6. And the other 3 projects that I've been involved with, we've all had great success with the air leakage management. We just put a lot of time and effort into it, planned it out, and just were really anal about it, executing it, and it really paid off. We got really, really low levels. In fact, I thought the 0.3 on the latest was kind of the best in Canada, but I think there have been several that have been below that already. So that's good. It's one of the most difficult things. It's not difficult. It's one of the things that builders are least accustomed to. It's just being aware of where the air boundary is on a house, where the air barrier is, and to making sure that it's been completely integrated and completely sealed. Okay, I just want to talk a bit about the space conditioning inside. So again, the main feature about the house is you have extreme thermal comfort in all 4 seasons. The temperature varies very little from floor to floor or from the southwest corner to the northeast corner. There's a very, very stable temperature. I have temperature sensors all over the house. In fact, the summertime profile is very interesting. We have, I think I have a picture of it coming up here. Let me finish the rest of this slide here. It just says, relative humidity, there is actually no active humidity control. It's just a natural state of affairs. Through the ventilation system that we have is always in the 50 range, which is very comfortable, especially in the wintertime. Some of the spaces are on the hottest days of the year do require the intervention of ceiling fans, which are, again, a pretty low energy way to increase comfort. This is the main heating system of the building. There's 3 zones of baseboard heaters. And again, I would do this differently now, and I have done it differently, but at the time I was trying to keep the system as simple as possible. Electricity is an expensive way to heat if you're going to use a lot of it. If you're not going to use a lot of it, it's actually not that expensive, and it's certainly a very easy system to put in. So that baseboard heater there has no moving parts, right? Like, unless I really take the dining room chair to it, it should last a really, really long time. It's connected to a thermostat, which makes sure that it only comes on, or tries to mostly come on during off-peak hours. So it can be programmed that way. This is a Mitsubishi air source heat pump. This is the compressor. It's on the outside of the building. And this is the air handler, which is on the inside of the building. So this is located on the 2nd floor in that dormer that you saw. And this particular air handler can heat or cool the space. And it's a 12,000 BTU unit. It has the capacity to heat and cool the entire house. So in cooling mode, I'm not sure if you're familiar with these units, but they're very common in Europe and in the Far East. And basically what they do is it draws the air in off the ceiling, passes it through a fan coil, and either heats it or cools it depending on the mode it's in, and then blows it back into the space. So it just circulates the air around and around. In cooling mode, from the 2nd floor, it actually slowly permeates throughout the entire house, and it is very inexpensive to run. It's very quiet, and the first summer, like on the hottest days, because we didn't have the ceiling fans, we found it getting warm a little bit in some of the bedrooms. So we got ceiling fans to mix the air up, and that made a big difference. In heating mode, it has enough capacity to heat the entire house. If I could heat the house with this, I wouldn't need to ever use the baseboard heaters. Unfortunately, the physics of hot and cold air are different, and the buoyancy of hot air means that the air does not want to leave the top floor. So I haven't figured out how to get the warm air that is generated up there to the rest of the house. I've tried ceiling fans. It isn't going to happen, is the bottom line. So we've ended up using it very little in the wintertime, simply because it just overheats the space. So we run it for a little bit. It actually accounts for less than 10% of the overall heating profile from a cost standpoint. But it's an excellent system. In subsequent homes, I've added multiple units of these, one lower up down in the building for heating and one higher up for cooling. Okay, so the mechanical summary. So there's no gas in the house. All the appliances are electric. There's about 5 kilowatt hours of baseboard heaters and in-floor heat, which we roughed in at the same time. Multiple zones with programmable thermostats, and the Mitsubishi system that you just saw there. As far as the energy goes in the house, one of the biggest energy users, especially in a high-performance house like this, or in an ultra-low energy house, is heating water. So we heated water for the first while with just a straight electric tank, but this past year we've installed a heat pump water heater, sort of the newer generation of water heaters that are coming on board. And I've been monitoring the consumption, the energy consumption of that quite like daily since I installed it about a year ago. So I'll have data on that coming up. I don't have anything on it right now, but so here's how it kind of plays out. This is the demand by heat zone for the last 3 winters. So you can see that the basement draws the most amount of heat. That's the green band on the right-hand side. The yellow band is the little, we have a small baseboard heater in the main floor bathroom. The red band in the middle is the Mitsubishi unit. That's the split heat pump. And the blue band on the left-hand side is the dining room baseboard heater on the main floor. So you can see that the basement is where most of the heat is called for and is generated. Obviously, by convection, it travels through the rest of the house and reduces the demand that the other systems use. In 2015, I actually did an experiment. I tried heating my entire house by using just a radiant floor heat in the basement. So when we did the renovation, we took the basement slab out. We put in 4 zones of pipe in the floor, and then we heated it with electric resistant water tank this past winter. And I was determined to heat the entire slab and the entire basement floor to 20 degrees. I just wanted to do an experiment. I started that way when we turned the system on at the beginning of November. Drove my wife crazy, but we heated the whole house. I wanted to see exactly how much energy I'm going to use if I heat the basement to 20 degrees, because all of the comfort parameters for passive house are around 20 degrees Celsius. So anyways, I ended up using a lot more energy. And the upper part of the house, you can see that in the middle, the Mitsubishi unit didn't come on at all. I think I only turned it on to demonstrate to people coming to see the house. It just got too hot on the second floor. It was like maybe 21 degrees, which doesn't seem like hot, but actually when you're trying to sleep in the wintertime in a house that has uniform temperature, it's actually too hot. So it was a little bit uncomfortable and unnecessarily expensive, but now I know. So this is kind of a cost summary of what I've actually encountered. Now I measure the power of my heating system through a system called TED. It's called the Energy Detective, and it's a web-based monitoring system that's actually connected at the other end, at the business end, right into my electrical panel. But the cost per kilowatt hour that you see there is creeping up. It was 14 cents in 2013. It's up to 16 now. That includes delivery. That includes everything. I'm a real champ at using electricity off peak. Our bill is like very, very, very stingy as far as peak electricity goes. Yet my average rate is still what I've displayed there. When I take my total kilowatt usage by my cost, that's what I get, 16 cents a kilowatt hour. So the total kilowatt hours used for the heating system, now this isn't for the whole house, this is specifically for the heating system. You can see in 2013, 3,003 kilowatt hours. Not that cold a winter. Remember 2014, that was a really cold winter, and so was this past winter. So you've got 3,800 kilowatt hours and 4,400 kilowatt hours. If you look at the line below that, this is the heating degree days. Okay, heating degree days are it's the measure of how do you describe heating degree days, Greg?
The cumulative degrees from 18 degrees.
Exactly. It's the amount of heat away from 18 degrees that your house needs to make up for to keep it at 18 degrees. So it's a good measure of the coldness of a winter. That's good. That's a good scientific way of putting it. So if you can see that in 2014 and 2015, they're basically the same. In fact, it was actually less in 2015. So the 4,400 kilowatt hours I used versus the 3,800 the year before proved that it was 10-15% more costly to keep the entire house heated the way that I did. It was a worthwhile experiment, as I said. But anyways, the total heat cost, if you multiply the total kilowatts by my average cost, you get the total cost for the year. So my heat cost for 2013 for the entire heating season was $420, $570 in 2014, $712 in 2015. It doesn't sound like a lot. I suppose there's a lot of higher heating costs around there, and there's probably lower ones. But I will say that if this is all straight electric resistance heating, if it was supplied with a heat pump, it would probably be half of that. So even at $700 for last winter, it's still barely $100 per month. So I'll bet you a lot of people's gas bills were more than that. And if you look at the bottom line, you can see what my gas bill was. It was exactly zero. So in cooling mode, it's super stingy. There's the kilowatt hours used for the cooling season and the cost as well. This was a little bit of a hotter summer at 81. Oh, I know there's another thing I forgot to mention. My mother, my 82-year-old mother, lived with us for part of the winter in 2015. And I didn't take account of what an excess drain on power that was. But there were parakeets and monkeys living in her room, so I think she was really, she had like spare heaters. It would just not get the room hot enough. I guess when you get older, you need a lot more heat. But that put a drain on things for a bit. But let's just say that it was all a good lesson learned. So I don't know that I have a whole lot more to say about this. I think that's pretty much it. I've just tried to hammer home the point, or just to make the point that the comfort that the house has afforded us and the ease of operation, the fairly low operating costs, I think have been totally worthwhile. I feel that the work and the effort have been totally validated, and I'm really excited about it going forward. I think the expectations surpass what we originally thought they were going to be, and I just would like to see the whole concept adopted on a wider basis here in Ontario. There's a lot of capable, enthusiastic people ready to deliver that, and I just hope it happens in 2016. So great, thank you.